Hi everyone, welcome to MathSpellBook. I'm your host Peter, and basically we are just going to get into, I guess, a little bit of proofwriting, since I have been lacking on doing those in a while. So usually proofwriting, it takes me a lot longer to solve these problems because I have to think a different way to actually solve these problems. So that's usually like how it'd be, and sometimes I'll be looking up definitions and scrambling about, so hopefully you guys enjoy the struggle. Of course, people that love math or love physics are used to it. They're used to dealing with the struggle. So hopefully you guys are doing well, and happy Labor Day to all of those who are living in the States. Usually Labor Day, everyone gets a day off. So hopefully you guys in the States are enjoying your day off before, I'm guessing, basically the school year begins. So, if you're actually going back to like university, or you're going to university for the first time, or if you're going to grad school, you know, that's also another thing. So like hopefully you guys are having a good start if you guys are just starting out. Going back to school if you're not living in the States. But if you're living in the States, hopefully you enjoy your days off before the new semester begins. Anyway, but even if you're not in university and you're just working, you love math as a hobby, hopefully you're enjoying your day off from work if you're living in the States. So, let's see if A and B are boxes. Usually I always struggle with the De Morgan laws, so I think we're going to focus. Let's see, if A and B are all boxes, possibly with things inside, describe the following terms in the boxes. Well, I mean, if you were thinking of the union of the whole thing of this, then because I mean it's every single element in here, so I would think it's like you can't really like say it equates to like one. It basically is all of them at that point. But for the intersection, I think the intersection is basically it's all the way up to A1 at that point. So let's just copy this. Paste it, disallow. So we'll just do it like this. Okay, so I think I'll go back into the book. Oops. Hey, how's it going, Zach? Oh, I don't have my. Let's see, where is it? There it is. I thought I had it there. Happy Labor Day, Zach. How's your Monday going so far? If you guys are not familiar with Zach on Twitch, I will give him a shout out. Zach is another math streamer and an official mathematician. So if you have any math queries or you just want to learn more awesome math, be sure to check out Zach out on Twitch. I always give Zach a shout out because like he got his doctorate this year, so now I can officially call him Prof. I'm no more a mathematician than you are. Well, but you know a lot more stuff though. I mean, I'm pretty sure if you look at the question I'm dealing with, you're probably thinking, oh, I've done this many times. For me, I'm like, oh, I still haven't. It's like those feelings where you're like, you know what 2 + 2 is, or you know how to solve like for the roots of the quadratic formula. Like for me, like I want to develop where it's like, oh, I know how to do this, but like for me, I haven't developed that yet with proofs. So okay, prove that the union of B complement is okay. So what does it mean for it to be a complement of something? Maybe it's true in some areas, but I'm sure you know things that I don't. The weird thing is with me is that when I start learning math, like if there's like a physics application to it, I probably remember it much better. So let me show you an example, because actually I thought this was a very interesting one. Because like in physics, they basically say it's the more math you know, the better it will be for you. I didn't fully understand that until I actually encountered something with periodic simple harmonic motion. Where is it? There was an interesting example they gave here. Here we go. Yes. So the vibration of molecules. I thought this was a very interesting example because you see all this complicated math they're doing to basically get the potential for, well, like if you guys don't know what potential energy is like the energy that could be in the system that can occur, and then it can be converted into kinetic energy. So energy that we can, I guess, visibly see taking motion. The interesting thing is that in this part, when they're trying to make it fit with the simple harmonic motion, well, Hooke's law, actually, the way they break it down is basically using the binomial theorem, which I thought was really cool. And then I kind of came to the, I guess, the epiphany where it's like, the math techniques are great as a toolbox because there might be a mathematical conundrum you encountered within, I guess, trying to do it the way that physicists know how to do it, and then suddenly like, oh wait, it looks similar to this mathematical technique that I've observed in a class that I've taken, so I can implement it and see if it comes out to be the same type of physical law that I've gotten used to. So I thought that was pretty cool. That's like one of the examples, I think, that kind of makes math come alive for me. But if it's like something very abstract, that's when I have to actually try to visualize things and try to build things. I try to build an intuition to it, but at the same time I have to have like a graph or something visual. So I think we can go. The problem is that this doesn't have I don't have a bookmark section, so I am gonna have to rummage through the pages here, like the old-fashioned way. So they show complement here, or at least the definition, so I can actually have a clear. I guess not. So I guess I'm gonna have to go to the book of proof. Fundamentals. Let's go to sets. I just want to have the exact definition so I don't have to like write it out. Complement, subsets. Well, we'll take the definition of union and differences, because I think that would be necessary for this. Because usually when I do proof-based questions, I sometimes don't read clearly well, not clearly, the word is, I don't utilize the definition very well. Like, I know it, but then I don't utilize it, and that's the thing that I have to, like, get used to. Because a lot of times when I do these proof-based questions, a lot of you guys basically tell me in chat is like, focus on the definition, and I'm like, I'm reading the definition, but maybe I'm not utilizing it the way you guys see it. And I usually know that it's a me problem when it comes to that. Because it's one thing to read the definition and know what it says, or that's not the right way to phrase it. It's one thing to read the definition and actually kind of memorize what the definition is saying, but it's another thing to actually be able to read it and then utilize it to the way that they expect you to, if that makes any sense. Or what you can use, what kind of fun little things you can do with it. Because, you know, with the definitions, there could be a little bit of a loophole you can, like, exploit to basically make it make sense. Ooh, the division algorithm. Where's the complement? I know I could do the simple way where I just do search and then just like search for the word, but I'm like, I feel like I'm enjoying the rummaging through this a little bit more. Okay, we got empty set, subset. Where's complement? They usually have complement in here. Oh, I probably should have done that. But that's not what I'm looking for, though. Am I thinking of the wrong term? I'm probably thinking of the wrong term then. Maybe some differences here. Because I'm pretty sure complement is the thing when it has a little c, isn't it? Unless this is another way of denoting complement. Denoted universal. I'm thinking this is it. I thought this book used oh yeah, these are the primes. Okay. I mean, it's not the primes. It's supposed to be not the primes. It's the natural numbers that are not prime. That's what it's supposed to mean. Okay, so I guess this is a complement. I guess the book is using the C version, whilst I'm using this book is using the dash line on top. Okay, so I think those are the definitions we're going to have. So the first thing we're going to have to prove is that the complement when A intersect B is not when it's not in the intersection of these two, that it is a complement of A with the union of the complements of each other. Okay, so I think what we should know is that for the intersection, this is probably the scratch work I'm doing beforehand. So A and is an element of B. Now for it to be a complement of A, basically, I think it's just, you're just given that X is not an element of A, and X is not a complement of B, and for the union of the two, that is an element X such that an element of A or an element of B or both. Okay. Alright, so we have our definitions laid out. So now, basically, now we gotta figure out how we're going to do this. So I'm guessing for the complements of these two, we're gonna have to use like different variables. So now the hard part, actually writing this stuff. So proof. So now, probably I'm gonna have to start with the left side. And then we're gonna have to show that the right side is equivalent to the left side. So let X be an element of such that X is an element of A and is an element of B. So definition of a complement, let Y be an element of such that I think if it's the complement, then basically you change the and to or, is it not? Right? Because it's supposed to be not. Because for a statement it could be and or, right? So if it's not and, then that means it's or, right? I think. But then we can probably write but not both. Can we? I mean, because technically it's not supposed to be in the union, so I mean in the intersection, so but not both A and B. Maybe I should put but not in both sets A and B. I don't know if I wrote this right. Yeah, the thing about math proofs is that you have to make sure that everything's airtight. And now I'm questioning whether this section here I wrote is... I'm not sure if that's the right way to write this. The thing with the union is that union includes both, but it's basically like it can involve both, but it doesn't have to. Unless I take this part out. I mean, technically a union would include everything in the intersection, but it's not the... I think like the not part, or the complement part, is like, it's supposed to be not the intersection. But if it's not an intersection, then it must be like a union of the sets, I think. So I think it might still work. We probably just don't need this line here. Okay, so now we gotta show on the other side. For the right-hand side, I'm pretty sure mathematicians, like, they shorten it to this, right? If not, then I'll just write it all out if that's not appropriate, especially for someone who's very new to proofs. actually needs one variable, so we have x is equal to, or x is an element of b. Okay, so actually, definition of a union of sets X can be in both A and B. Thus, X can be an element Okay, but if x is in a complement, then it is in B, and if x is in B complement, then x is in A. And by definition of a union of sets, x can be in both A and B. Thus x is in the union of A and B. So the way this is that because the way we prove this, it just feels like we proved it by the opposite standing, because it's like basically it's about the complement, right? So when we did the complement for this side, we basically got the union, and when we did the complement for the union, then we ended up getting the intersection. Now, I'm wondering if that is actually the right approach we were supposed to take with this. Because it feels like it's the union. I mean, it's the intersection, but it's the complement of the intersection between the two. And then on the other side, it's supposed to be the complement and the union of another complement. I feel like it is right the way we wrote it, because we got I guess the quote-unquote complement of the union and the complement of the intersection, because that's what we wanted. I think it's just to prove that these two are equivalent, and it seems like they kind of are, because they're actually doing the opposite of one another. If, you know, intersection is the opposite of a union in this case. Because it feels like it connects. But like whenever I write an essay, like I think I write something that I think connects, but then there's so many like logical plot holes that I didn't include. So I feel like we did the right approach, because at first I thought we had to kind of show every little detail in here, but it seems like the way we did it was like kind of like proving that the complements are the complements of one another. So I feel like that was the right approach. But of course, like if you guys are like more literate at proofwriting than me, you can tell me if I'm wrong here in that case, because I feel like that's what this proof is meant to show us, is to show that the complement of this is the union and the complement of this is the intersection, which is why they're equivalent, I think. But then again, you have to show that the right side is equal to the left side, I think, which is probably what I didn't do. Yeah, probably I didn't do it right. Usually this is like based on our own study and research, so we worked pretty intensely on that, but let's see what ChatGPT says about it. Oops. I didn't mean to copy all that. Wow, that's like a lot of stuff. Just want to erase this whole thing. Don't tell me it's like a long amount. Let's refresh here. No, I don't want to get rid of all that. Okay. Let me go back here. Maybe we can just recopy the question. It's a lot shorter than what I wrote. What I wrote, it felt like a long paragraph. I've done this before, so maybe I can try it. Wow, I hate it that the toolbar's there and I can't get everything, so maybe if I minimize it like that, and then I don't know if it's going to be able to read everything. No, because I missed a little bit here, so maybe we'll just shrink it a little bit more. Then no, I'm gonna have to do it higher, like this. Yeah, there we go. here. So according to ChatGPT, I just basically expanded too much on one definition compared to another. Firstly, okay, so basically the way they're telling us is to write it like this. Okay, so since we didn't really get this proof right, because I extended it a little, a bit, and I didn't make any logical connections. So I guess we're gonna have to practice with the next one. So the next one is A union is the complement equal to okay, so proof. Let X be an element of the intersection of A and B complement. Therefore, X is not an element of A or X is not an element of B. is an element of B complement. Is an element of A complement, and well, actually, we should write this first part first. Thus, A is an element of A complement, and X is an element of B complement. Definition of an intersection of sets, X is not an element of but it is an element of okay, I think we got the hang of that. Therefore, oh yeah, it is. Let's erase this. That's not what we're supposed to do. also have the universal set. Because we have to find a way to turn this intersection into a union. So this is the definition we're given. So x, and that means that x is an element of A complement, and then x is an element of B complement, meaning that x is not an element of A. X is not an element of B. about this. It's like do the algebra and then you end up with this funny thing. But then that doesn't mean anything, so But sometimes with the math, like sometimes you can just play around, see what works and what doesn't. Technically this would be an intersection because it says because this would be like complement a and I feel like there's a connection because I don't want to like look at the ChatGPT stuff because I know it's gonna tell me exactly how the setup is gonna look like, but I'm trying to think about how I can set this up because I kind of remember what it said like for the first part, which is basically like you have to write it like it's not part of this set here because that's what the complement is. But now we have the complement of these two things. So now we just have to figure out how to use these small parts to give us the next part, and I think that's where I'm blanking out at this section here. So because we know that x, when it's not in A, x is not in A, and then x is not in B, which is what the intersection is, but at the same time it's like it's also telling us something else, which means that because if x is not in both A and B, then it has to be part of the universal set. But I know that's not the way we're supposed to go about it. So I kind of missed it here. For this one, yeah, this one was a little bit easier, but this one is just, I had to like find a way to think about it more. I didn't know how to write it, that's why. Yeah, that's why proofs are like very, very hard. Because, like, for me, it's like, the way they write it is so, like, clear and concise, but, like, for me, it just feels like I'm just writing nothing but gibberish. But, you know, that's how it be sometimes. Okay, so now I think I'm going to go into a little bit of complex analysis to see what I can gather. And this book is called A Friendly Approach to Complex Analysis, so I thought I would check it out. Because whenever I open a book about complex analysis, it's like they always reintroduce complex numbers, which I understand why they do it. Excuse me, but I feel as if like I want to be able to see beyond just the regular arithmetic. Let's see, complex numbers and their geometry. In this chapter, we set the stage for doing complex analysis. We study 3. Okay, introduce the sets of complex numbers with their arithmetic, making C into a field, expanding the usual field and real numbers. Okay. Points in C can be depicted to the plane R2. We see the arithmetic correspond between. Okay. Finally, we'll study the fundamental function in complex analysis, namely the exponential function. We'll also look at some elementary functions related to the exponential function, namely the trig functions and the logarithm. Okay. Product of these two. Okay, Albanian group. So the complex numbers without the set 0 and multiplication. Okay. Distributed holds. Let's see, an F1 Albanian group just means the operation addition on C is associative and commutative. There exists an identity element such that, okay, for all x and y, every element x and y has an additive inverse. Okay, similarly, F2, multiplicative identity of complex numbers is the complex numbers without the ordered pair of 0, 0 is given by, okay. Exercise 1 check. 1, 1 is indeed the inverse of. Let's see, R is contained. Oh, this is for the cubic root. Let's see. Very interesting. These two will cancel out, leaving us with minus, well, actually plus. That leaves us with like just nothing but real numbers at that point. That's exactly what they wanted. Let's see. Check that 1.1 is indeed the inverse of Hey Jose, how's it going? Just reading through a little bit of complex analysis right now. We did like 2 proofs like earlier today, but unfortunately I was falling short of the definitions here. Not very formal. Not very formal in my writing of the proofs. Starting a new university here? Nice, nice. I forgot, Jose, what were you majoring in again? Did I do this right? I probably did do this right. So the way they do multiplication, I think, is different. So it's like supposed to be x times x2 minus y2, and then the other way is the opposite. It's like right? Yeah, that's the way they did it. So I think the way we did it wasn't the correct way of doing it. So in this case, we have x times x over x squared plus y squared, then y times y over x squared plus y squared. That's the first part, and the other part is basically just adding them together. Now I'm on my 3rd year bachelor's degree. Last one before a master's. Nice. Nice, nice. Oh, so you're majoring in math, right? And hello, NY Lonco? I'm pretty sure you've tuned into our stream like probably a couple times, because it's not the first time you're I don't see like it's the first time chatting icon over your name. But how you doing, NY? Hopefully I'm pronouncing your name right. Hard to say. I tune into math streams here and there. Yeah, okay, that's fine. That's fine. Well, glad to have you in. Are you starting like this new school year for yourself too, or are you just like looking math as a hobby, or you do math like you do math in your actual job? Because the new school year is starting, so you know everyone's gonna get back to study mode. Now, yeah, I went undergrad pretty far in. Oh, nice. What are you majoring in, and why? Is it math or is it like something else? Program the first semester, measure integration. Oh wow, topology, mathematical analysis, differential equations, complex analysis. Nice, nice. Okay, so everyone's math here. Yeah, like at the beginning of the stream, I was actually just doing two basic proofs. You guys are probably already like, oh my gosh, I couldn't solve this in my sleep. But I had a really hard time with this. It's like the typical like De Morgan laws, and I was like, oh my gosh, like the first part I was overcomplicating it, and the second part I was close to finishing this part, but I got stuck here and I couldn't figure out how to turn this part into this part. So I mean, I know it's part of the struggle with proofs, but at the same time, like the amount of times I struggle with proofs, I end up wondering, it's like, I mean, I like math with physics, but at the same time I'm like, should I study math the way physicists study math at this point? The only proof for De Morgan laws that doesn't trip me up is using use the indicator functions. What are those? I've never heard of those. Yeah, cause like I did find a course on like what was it? Geometric algebra. And apparently, according to the person's description, they said that you need to know like linear algebra, and maybe some basics of calculus. But as soon as they got into like the stuff like involving wedge products, or exterior products, whatever you want to call it, I was like, what is this? I know it's supposed to look like this, where it's like you have a vector here and a vector here, and it takes into account the orientation and the area of the space, and it's supposed to kind of replace the cross product. But the one thing is that I know with the cross product, like when you have the cross product, I should put arrows here, right here. I know with the cross product, they give you a way to solve it, such as like, you know, like doing the determinant, and you know, A1, A2, A3, and it's only defined by three-dimensional space. But with the wedge product, I'm like, how do I break down the components of this? That's the one thing. The only thing I understood about it was that it's defining this, but I'm like, how do you get the direction? How do you get the area? And I'm like, how do you get the components of this? like the person that's like teaching the course, like they didn't really explain it much. All I know is that the wedge product means this. The only oh, okay, I already read that. Or characteristic function. My bad. Indicator functions are different. Oh, okay. exterior product are awesome and dot products are terrible is terrible. Yeah, I see that. I did learn the limitations of you know, the cross product and the dot product. I know the geometric product is like A, B, and then A dot B. Maybe I should put vectors up here. I don't know. Plus the wedge product between these two. Like, I mean, I know how to get the dot product, but I'm like, how do you break down the wedge product? Like, how do you actually turn it from, because with the dot product, with the cross product, you know it's going to be either this way or it's going to be written like this. The one thing is that, like, how do you break this down? Like, all the person that said that teaches this course is like, this is the wedge product, and I'm like, okay, so how do we break this down? Oh, hey, and Stunky. If you guys are not familiar with Ed Stunky, I'm gonna give him a shout out on Twitch. And Stunky is another awesome math streamer. He also programs, so if you're into like computer science and stuff, you can definitely check out his stuff to see what he's programming. Yeah, there we go. Okay, cool. I'm looking at this book after you mentioned it. Looks very nice. Which book are we talking about? Same way that understand vectors, you use the basis with x and y components. To understand a bivector, you use the bivector basis. Yeah, I got confused when it came to bivectors. So you write it in terms of the unit square in the xy plane and the yz plane and the xz plane. Complex analysis, one you're reading right now. Oh, okay. Although it's even though it says friendly approach, I probably have a long way to go before I can actually read this material. Yeah, because like I end up asking Sascha like which he was researching, because I thought he was researching geometric algebra, but he was researching algebraic geometry, and then I had to look up the difference between the two. I mean, like I find the stuff I'm learning in the geometric algebra stuff cool, but at the same time like the wedge product and stuff, like the new stuff that I just kind of got exposed to, I started like thinking like, wow, this is cool, but at the same time I'm like, how do I do problems involving these? Let's see what you guys type up. It's a lot easier to see that than to read over Twitch chat. There's a series of YouTube videos done by okay. I'll just definitely copy this. I'm just gonna put this in my notepad. Just call it math. And also, if you if you want to actually post resources, you can basically do that in our Discord server. So this is our Discord server. If you want to actually join our Discord server, it always helps me to know what content you guys like recommend for me, because for me it's like I don't have a really set order, which is probably bad. I don't have a real set order of like what I read about or what I study about. It's just that if I'm interested in topology, I'll read a little bit of topology, even though I know I'm not going to be able to solve problems involving those things. If I'm interested in real analysis, I end up reading real analysis, but I still fail at the problems. So, you know, like, I do like reading definitions. The definitions like density and all that stuff. I'm like, oh, that's what density means in math. I think like density in science is different. Like I think it's like mass over volume. I think that's what it is. Anyone who's like a physics or like science major, please correct me if I'm wrong about that. But yeah, like like Sascha is researching algebraic geometry, and I was like, oh, okay. And then when I started talking to ChatGPT, I'm like, is there a relationship between geometric algebra and algebraic geometry? And then like when it said that basically, oh, there's like a lot of relations with physics and stuff, and I'm like, oh, okay. So I thought that it would be pretty interesting to like see what both of them have to offer, you know. Geometric algebra, algebraic geometry. Yeah, like Sascha told me that like geometric algebra feels kind of cult-like, and then when I had to type up both of them in Google, I saw there was a lot of memes about it. Like either people thought that geometric geometry is like really, really cool and abstract, but it was like it's really hard, like what the end result is when you actually prove things. Whilst in algebraic geometry, I saw that it's like it has a really big learning curve, but it does give things in a more, I think, how should I think what I've seen is that it's supposed to give things in a more simplistic model, even though it's like it has a higher learning curve than geometric geometry. But both of them seem very, very hard though. I mean, I don't even understand like the wedge product here, like and the geometric product. I'm like, and then when I started learning things like bivectors and trivectors, and I'm like, okay, what? It's like, how am I supposed to do the technical calculations or the technical math involving that? But I probably should get back to this, because what Sascha told me was that if you want to learn algebraic geometry, it's better for you to know, you either do it by learning analysis or you do it by learning complex analysis, and then oh no, not analysis, algebra, sorry. You either do it by just learning pure algebra, or you do it but I'm not, when I say algebra, I don't mean high school algebra, I mean like actual math proof algebra. You learn it through like algebra, and then or you can do it through complex analysis. And I'm like, oh, okay. So and the weird thing is that I think for me, I learned math better like through the eyes of non-mathematicians, which is probably bad because it's like mathematicians can get to the real deep heart of what it means for a mathematical object to be a mathematical object, which is something I'm interested in. But the way I learn is that I feel like I have to learn as if like I'm just fiddling with actual tools in my hands. But you know, what do I know, right? What do I know? Let's do some algebraic typology. Is that are you just joking around, or are you being serious about that? Jose, let's see. Algebraic geometry seems to have acquired a reputation for being esoteric, exclusive, and very abstract, with adherents who are secretly plotting to take over all of the rest of mathematics in respect. This last point is accurate. Interesting. And I'm guessing you're quoting someone at Stunky, because you put, let's see, David Mumford. I think that's how it is with physics too. It's like they basically saying like string theory is basically the, I guess the, it's not toxic. I don't want to think of that word. Something that's sort of like it doesn't go away, but you know it has to be there regardless. I'm not saying like, you know, like I'm against string theory or whatever, but I think that's how some physicists that don't like string theory say about string theory. It's like, it's there, but we can't get rid of it. But yeah. Not now. I don't want to lose my brain trying to understand algebraic topology. If I'm not studying cohomology in a year, I'd fail myself. What is that? What is that NY? I've seen that word so many times whenever I read like mathematical texts, and like if you can give it to me in like say with someone who has a knowledge of just basic calculus 1 and calculus 2 knowledge, like that, I would appreciate that, because I've seen that word so many times, and because like when I read the word like isomorphic, it took me a while to like get used to it, but I never fully understood what that word meant either. And I had to look it up, and sometimes when I look it up, I end up forgetting what it means. But I hear it all the time, or like I've seen it all the time, like in books. Let's see, the geometric meaning of multiplication. Technical definition is not gonna go well, so it's roughly studying the failure of local properties of a surface to hold globally. In some sense, by studying the holes in a surface. Okay, I see. Okay, so it's the same stuff that they talk about in topology then, like how many holes something has, and it can make an object based on the amount of holes that it has, right? Like if you have like one hole, you can make it into a mug or a donut. And I'm guessing if you have 2 holes, you can probably make it into like maybe like a 2-hole donut, or like what else can you make with 2 holes? Yeah, actually, like Hodge's conjecture. Yeah, like it's kind of funny because where is it? I don't know if I have it here. I probably don't. I probably don't have it. Let me see here in my other screen. No, I don't have it. Okay. I had a book on algebraic geometry like on my browser before, and they were talking about Hodge's I think like Hodge's like conjecture, like on the last part of like the last part that they say they were going to cover in chapter 1. And I was like, wait a minute, I remember Sascha was researching that. Let's see, divorce formula. Yeah, it ties those holes in algebraic properties which are invariant under continuous morphing. Okay, so I'm guessing like when you say continuous morphing, you mean like, let's imagine that like the manifold is like a piece of clay, and when you say continuous morphing, I'm imagining it being like a bulging slime that basically just pulsates until it forms something, I guess something concrete that we can see, like a donut or something, right? Is that what you mean by continuous morphing? Because I'm thinking of like something like that, like, you know, like you would probably see like in a computer simulation or something. Like it can morph a coffee mug into a donut, that kind of morphing. Oh, okay. Yeah, because like the way when you say morphing, I'm thinking about like, because I know with continuous it's supposed to be smooth, and when you say morphing, I'm like, okay, is it sort of like, you know, let's say if you have like a little blob, and like let's imagine that whenever you give it an electric pulse, it just basically just morphs into something else. Like I'm thinking of that. Like I'm thinking of like a little blob that basically is like constantly like pulsating until you give it a nice spurt of energy or electricity, and then suddenly it just morphs into something, whatever you want, in some ways. I guess you can think of it as sort of like mathematical alchemy in your head. Yeah, I know I'm talking too much, guys. I probably should just be like focused on like doing more problems. But I think talking about this stuff with you guys makes it fun because it allows me to develop my imagination for like mathematical things, even though they're like pretty abstract. Continuous and smooth do mean different things. I'll caution, but yeah, I think you got the main idea. Yeah, because so what is it? So I know something can't be smooth, but it can be, but it doesn't mean it's continuous. So like, what's a good way of actually thinking about the differences? I mean, because whenever I think of something continuous, I think of it as like curvy and smooth. But then again, that probably is not correct. Because I know that you can have like, I think you can have a cusp, and it could be like, not really exactly a cusp, but something that's sort of similar to a cusp, and then like it's considered continuous, but it's not differentiable. Or I'm probably getting the example wrong, but smooth tends to be implied differentiable as well. Okay. Yeah, it's actually funny that you mentioned that, Jose, because I actually saw that in the first page of the algebraic geometry book I was reading. I thought it's funny that you're mentioning the stuff that I've actually seen on the first chapter. I haven't read it. I saw like that on the first page. Let's see. What did you type? NY. Without other quantifiers, smooth will often mean infinitely differentiable. Okay. So if it's continuous, does that mean it's just differentiable to a certain point? Is that what it means? I mean, is that the difference, or am I just missing out? Basic examples. Oh, okay. Yeah, like whenever I look at math, I love looking at like the interesting symbols and equations and see how they work. The thing of it is that there's like math vision and there's like physics vision, and I think for me, I can't really develop my mathematical intuition until I have the physics vision in it. I mean, like things like distance and like metric, like I think that's also intuitive for like anybody, regardless of whether they know physics or not. But at the same time, it's like when it's like very abstract, that's when sometimes you get lost in the weeds. Oh, okay, we got some exercises here. What are the exercises? Where's the first one? The first one here. Let's see, exercise 1.22. Let's see, continuous doesn't formally imply any notion of differentiability, but a lot of examples of continuous behavior we care about are also differentiable. Okay. So now I gotta think about what does it mean to be continuous but not differentiable? I think there's like one example where I think Sascha showed me. It was like a graph where it's like it looks something like this, I think. Something like that. And I think like obviously I'm drawing this very badly, but it's sort of like something that looks like this. Like imagine that all these like mountains that I draw are the same, but they're considered continuous but not differentiable. I don't know if that's the proper way to address that example. But I think Sascha showed me that once before. Okay, basic example, you can continuously morph the surface of a cube into a sphere. Think about it inflates, that inflates continuous. Yeah, because it has no holes, right? So that's why you can turn it into, like, from a cube to a sphere, right? However, that map isn't differentiable at the corners or edges of the cube because they are sharp corners, right? Oh, okay, so alright, so like I think I'm starting to get a little bit of what you mean. So continuous but not smooth. Okay, so let me just reread what your example was. So you can continuously morph the surface of a cube, okay, its surface, into a sphere. Think about inflating it, okay. That inflating is continuous, okay. However, that map isn't differentiable at the corners or the edges of the cube because they are sharp. So continuous but not smooth. Okay. So you're saying that the moment of its inflating into the ball, or at least the sphere, is the act of being continuous. So like I'm still thinking about like still graphs and stuff, and I know that's not the right way to view it because you're giving a very great example because I can visualize it. So I think we can draw it. Where did I put my pen? Oh, there it is. So we have a cube. I know I'm not the best artist, but I'll try to draw it as like clearly as I can. So we'll inflate it with air, so let's just draw a little circle around it. And I think if we draw the sphere a little bit, let's just pretend it's still midway cube, so let's have the little corners poke out. We'll draw them here too. We'll just draw dotted lines here just to show that it's still the cube a little bit, but it's still being inflated. Oops, no, it's supposed to be that here. And then like that, like that, like that. Okay. So it's the act of inflating, so for some reason I'm thinking continuous is sort of like the process of actually making something into something else, if that's what you're trying to explain. You can make the same argument with the square and the circle. So it's the process of just changing it, right? So can we basically say that continuous is a non-linear transition from one state to another, or from one rate of change to another, if that makes any sense? Or a non-linear way of change, rate of change, I should say. Because I don't want to use the word smooth, because like when we say it's linear, that means it's like, I mean like it's going to be like constant, but I don't think the rate of change is going to be constant at that point, which means it's going to be a derivative. But then again, like there's also continuous where it's not differentiable. Like I'm just trying to basically break everything down, because like every time when like you guys talk about like complex stuff, I'm like, ooh, that's interesting. Like I wonder if there's like a way to explain it all. Oh, hello. Thesis Ordi? Is that how you pronounce your name? If I pronounced it wrong, please tell me. I thought it said Thesis Oldies, but there's an R instead of an L. Oh, Thesis or Die. Okay. So is it okay if I call you Thesis? But what's the best part of your day so far, guys? Like, I forgot to ask that when you guys jumped into the chat. I mean, I can dig into it, but maybe not well over Twitch chat. It's fine. That's why we have the Discord server. Find someone you're doing math. Well, actually, I was like kind of talking to you guys more than just looking to math. I probably should have done that, but I guess we talked for like the last half hour, because like the only math I did was basically trying to do the basic proofs. You guys probably think it's just elementary stuff, but for me, it's like still kind of hard. I was just doing these, the De Morgan laws, and I didn't do too well on them. I oversimplified things, and I could have made it simpler. When I did B, I actually was able to get this part here. But when I was trying to do the right hand side and getting it back here, that's when I got into a little bit of trouble. Even talking about, yeah, because like whenever you guys talk about like complex stuff, because a lot of you guys are like, I'm guessing like undergrad going to masters, or masters going into PhD, or just doing mathematical research in general. I like talking about it with you guys because it makes me feel as if like I'm getting closer to, I guess, like the academic mathematical world, even though I'm not doing a PhD or a master's or even a bachelor's in math. But you know, like there's a part of me that wants to learn this stuff because I want to get into like theoretical physics and stuff, just for my own education, not really for like a program or anything. You're doing proofs and working through problems, so you're already better than most. Well, I feel like I'm not doing well with proofs, and sometimes when I fail at proofs, I feel as if like maybe I shouldn't learn mathematical proofs because I'm more into the physics of math. Like I really want to be able to learn math so I can apply it to physics. But at the same time, like I know theoretical physicists, they do have to learn some mathematical proof writing to like, you know, get their thoughts straight. But at the same time, it's like I try to find like real world comparisons when it comes to like things like real analysis, just to make it come alive to me. I read the definitions and I find them very interesting. The problem is that I don't know how to apply those to actual proof writing, and that's what gets me a little bit doubtful of my attempts in math. I know that's part of the process, but at the same time, it's like it feels as if I'm kind of I feel like I'm not getting better with it, and at the same time, like I know I shouldn't think that way, but at the same time, it's like I don't know how to view it. But I think that's how every math major or every math student deals with it. I do find the definitions very enlightening, though. But at the same time, it's like, dang, I don't know how to apply them, which makes me kind of a little sad. If you aren't failing at mathematical proofs, you're not trying hard enough. Yeah, but at the same time, I don't want to view it as sort of like, oh, I got to get hard enough for some. Because I look at math as something that I would like to relax with, and like if I don't know how to solve it, I'll just put it down and try to like get my mind to something else. But I don't want to make it sort of like a military exercise where it's like, oh, if you're not doing math this way, then you're not doing it right. Because I don't want to think of it that way, because I think a lot of students get bombarded by that, and that's something that I don't want to put into my mathematical studies. I do like doing derivatives and like, you know, basic calculations. Those are fun. I think like when I do like basic stuff like derivatives and like I think I probably should do more trig substitution problems, because I did do some trig substitution problems while I was on break last week. No, not hard material. Even the simplest you learn by failing. Yeah, it's true. Because like for me, like I think what I find very interesting about math is that I really want to get into the stuff where it talks about like, you know, continuous morphing and topology and, you know, like seeing awesome, like really peculiar shapes and manifolds. Because I think like the math I want to get into when it comes to physics is like both geometric algebra and algebraic geometry, because I think those are the latest thing. Well, not the latest things, but I think those are the maths, I think the branches of math that I've heard that are basically benefiting theoretical physics at the current moment that I'm aware of, but there could be more because I'm not in the academic world. I want to be able to like actually learn those things. And you know, be able to explain, like if I'm able to like learn like understand things like the wedge product and the geometric product and explain it to someone that's actually like, you know, in taking linear algebra, then, you know, that's something I would like to basically, you know, give to someone who's really into this stuff, you know. I mean, that's I guess you can say that's kind of like my goal in life in some ways. Just learn the complex stuff to be able to explain to someone who's like probably like trying to learn this stuff as much as I am, but they're like at a younger level, such as like high school, or because like when I started learning math like on my own, I feel as if like, yeah, if I found this stuff interesting, like I feel as if like grade level wise, let's think of grades, not like I'm talking about years, like students' years. Like I would think like elementary school. Let's see, elementary. You know, arithmetic, and then you just go into algebra, like probably like algebra, like maybe like during 6th grade or something, like year 6, and then in middle school, like, you know, 7th grade to like 9th grade. Oh, thank you for the follow, Thesis. I really appreciate it. Yeah, if you guys like math or physics and like you're watching this either on YouTube Live or you're watching this on Twitch, you know, like please drop me a follow if you're watching this on Twitch. If you're watching this on YouTube Live, if you like math or physics and you just need a study stream to keep you productive, even if it's just me yammering, you know, drop me a sub, along with, like, you know, leave a like and a comment on the live if you're watching this after the live stream. But like the last thing I want to talk about is like basically like, yeah, you can do arithmetic, and I think you can fiddle in algebra like in the last maybe the last year of elementary school. And then I thought about it as like, oh, what if they did geometry and then they go into pre-calc in this part? Now, of course, like if this was the curriculum, I would have failed math like way long ago, because I wasn't into math at this point. I was actually lucky to pass these courses. But I only did like up to algebra up to high school. And then when I got to college, I think like the hardest maths I did was up to calculus 2. But I think like if you were to make the math curriculum a little bit more, I think faster, like, and you were to teach like, you know, the stuff like from algebra and all that stuff, I think in high school you can actually teach mathematical proofwriting, at least the basic version, like introduction to mathematical proofs. But of course they won't do it because I know it's going to be really hard, and they're going to be like, what's the use of learning mathematical proofwriting? Not everyone's going to be a mathematician. And that's usually how the school board will like basically argue about that. I mean, they're already arguing about like taking algebra off of the school curriculum because they feel as if like it's not useful, and they think that it's better for them to learn math for like data entry skills, like for those desk jobs, for data analysts and stuff, which is fine because, like, you know, if students don't know what type of job to get into, at least they'll have the skills to be like data analysts. But at the same time, it kind of takes away the creativity of what math can offer, which is unfortunate. But then again, but if you're gonna do that, like, make it an elective for math at least. Like, give them an elective to actually choose algebra if they want to take it, or calculus if they want to take it, you know? Okay, well, at least we did like 2 mathematical proofs today. I know I yammered like during the rest of the hour, but hopefully you guys appreciated that. And I also appreciate you guys basically sharing your knowledge with me on, you know, things like from like the stuff that you guys know, such as topology and algebraic geometry and all that stuff. Like, because whenever you guys say like a word that I'd never seen before, I ask about it and I try to learn exactly like what does it mean to be isomorphic? What does it mean to actually be continuous? Like, I love the fact that you guys are willing to like explain it and like give your knowledge away, like to all of us, actually, which is something I appreciate, because I'm pretty sure that if there is someone in chat that is at my level, like, you know, like, I feel like privileged to be like in the presence of like people that are actually like know more math than me and know more knowledge than me. But at the same time, like, if someone is like at my level, like, I try to ask these questions like to people that know the material, because I know you guys are curious about it too. But yeah, so I think that will do it for today's stream. We'll be back tomorrow. I know this was a little bit haphazard, like I didn't really plan this stream very well, but I just wanted to get into problem solving and like whenever you guys are active in the chat, I want to ask more about the stuff that you guys are studying or researching. So yeah. But yeah, thank you again, guys. If you're watching this on YouTube Live and you like math, physics, or you just need a study stream to keep you productive on your computer during the day, hit the subscribe button and, leave a comment and leave a like down below if you're watching this on YouTube Live. If you're watching this on Twitch, the same thing I just said before, just hit the follow button. It really gets me motivated to continue talking math and as well as like doing more math problems, even though they may be basic as heck. But I do get some people that are in high school and they basically ask me questions about vectors and stuff, and I find that very interesting. But most of the time I'm just like learning from everybody else. So if you don't mind like teaching what you know, or you don't mind just like, I guess, like educating a novice math hobbyist, like what is it that you know about math, just join the channel. And you can also join our Discord server. All the links will be in the description down below, and I think all the links I will type in the Discord server for the Twitch chat. You can join our Discord server so that if you want to talk more about the mathematical ideas you're exploring, you can put in our Discord server, and I will definitely read them, because usually when I'm active on the server, I usually like to read the stuff that you guys type up on what you find interesting. Okay, I think that will do it for today, guys. So always remember, everyone is precious. You guys are just as precious as everyone else. And I will see you guys either on the next stream, or if you want to check out my video game stream, my Uncle Talk stream, that's also going to be in the Twitch chat, and it's also in the description down below if you want to check out my video game stream. And I will be streaming on my video game stream tonight, so you're more than happy to join that, to follow me there as well. So take care, guys, and I will say it again, always remember, everyone is precious. You guys are just as precious as everyone else, and I will see you guys in the next stream. So take care, guys. Bye-bye.